So up to now we've been focusing on general equilibrium expressions and not really differentiating between the specific types of matter that are present in the chemical reaction. So are we in the gaseous state, liquid state, solid state, etc. So that brings us to heterogeneous equilibrium and differentiating between hetero and homogeneous equilibrium. So in homogeneous equilibrium, all the reactants and products are going to be in the same phase. So they'll all be gases, or they'll all be, dissolved in a liquid or dissolved in a solution and in the aqueous state. In heterogeneous equilibrium, we're dealing with multiple phases for your reactants and products. So you'll have some gaseous reactants or products and, say, a solid, or a pure liquid and some gaseous reactants or products. Now, what you need to understand is that with respect to your equilibrium, your position of your equilibrium does not depend on the amounts of either pure solids or pure liquids that are present in the equation. Okay, so if we look at this equation down here, notice we have two products that are in the aqueous phase, and we have obviously a solid reactant. So when we go to write our equilibrium expression for this heterogeneous equilibrium, we are going to exclude the solid. Okay, so in this case, PbCl2 is excluded, and we just report our equilibrium expression with respect to the two components that are not a pure solid. Okay, so hetero and homogeneous equilibrium. Obviously, if we have a heterogeneous equilibrium setup, we're going to have either solid, pure solid, or pure liquid present in the equation. We have another example here, calcium carbonate decomposing into calcium oxide and carbon dioxide gas. Notice that I have two solids, okay, one a reactant and one a product, and I subsequently have my gaseous CO2 product. So in this case, the only component that's going to be included in my equilibrium expression is the CO2. Now please understand, even though we exclude the solids and liquids from the equilibrium expression, it does not mean that their presence doesn't matter. The reality of it is that these reactants or these products have to be present in order for equilibrium to occur. It's just that their concentrations don't change, and because we're looking at equilibrium with respect to thermodynamic quantities and those activities, we subsequently exclude the things that are not in the same phase as either the gaseous or liquid setups. So the equilibrium expression, although it may exclude things that are part of the chemical reaction, please understand that we're not saying that they don't need to be present. Of course they have to be. So now that we've taken the time to differentiate between our hetero and homogeneous equilibrium expressions and how to appropriately write them, let's go ahead and let's look at calculating equilibrium problems. Okay, so there's a handful of steps that are required in order to basically be able to do these types of calculations. The first thing is we need to have a balanced equation. Okay, so either you're going to be writing it or it'll be provided. The next thing you'll do is write an equilibrium expression. Okay, and of course we need to be differentiating between the hetero and homogeneous equilibrium expression procedures. So make sure that you're excluding solids if you have a heterogeneous setup. You're going to then make something called an ICE table. Okay, and ICE in the I in the ICE table stands for initial. Okay, C stands for change. Okay, and E stands for equilibrium. Okay, and if you can remember that, you'll know what it is that you're going to be plugging into each space. Okay, after we make our ICE table, we plug in our appropriate concentrations depending on what we've been given. And then we plug in the E concentrations and subsequently solve for K. Okay, so we've been told that we have a closed system. Okay, so that's obviously one of the necessities for establishing equilibrium. And it initially contains 1.0 times 10 to the negative third molar H2. okay, and 2.0 times 10 to the negative 3 molar I2 at 448 degrees C. It's allowed to reach equilibrium. Okay, now analysis of the equilibrium mixture tells us that we have a concentration of HI that corresponds to the 1.87 times 10 to the negative third molar concentration seen here. Now they want us to calculate Kc, okay, so with the equilibrium constant at 448 degrees C for the reaction seen here. Okay, so we have our equation. All right, it's balanced. The next thing that we need to look at is setting up our appropriate equilibrium expression. So notice this is a homogeneous setup, so our equilibrium expression in this case is going to be HI squared over H2 and I2, both to the first power. Okay, so now that we've done that, we're going to then set up an ICE table so that we can figure out the concentration values for HI, H2, and I2 at equilibrium. Okay, so what you see here is an ICE table. Okay, notice I have my initial, my change, and my equilibrium. This is ICE, okay, as we've discussed. Okay, so ICE is what we're going to see here. And then what we have is we have our reactants and our products. Okay, so what we then look at is basically what the question has told us. So we were told that we have an initial concentration of H2 of 1.00 times 10 to the negative third. Okay, an initial concentration of I2 of 2 times 10 to the negative third. Okay, and of course, if the reaction hasn't started yet, we have a concentration of 0 of our product. Now, we were told that they analyzed the contents of the closed container at equilibrium, so once equilibrium had been reached, and they were able to obtain the concentration of HI at that equilibrium state. Okay, so now that we've set up our ICE table, we now need to look at the change that's going to occur in each of these steps. Okay, so we know that when we go from a concentration of 0 of HI to a concentration of 1.87 times 10 to the negative third at equilibrium, we know that we have gained 1.87 times 10 to the negative third. You can look at it, I guess, as moles of the HI product. Okay, so in that case, the change that's associated with HI is this value. Okay, so now we need to talk about the change associated with each of our reactants. And that's going to be related to obviously the quantity we see here, as well as the coefficients in front of each of these reactants. Okay, so stoichiometry is going to actually tell us how much our concentrations of I2 and H2 are going to change. Okay, so based on the stoichiometry here, the quantity that we have is equal to 2x, right? Because we know that the quantity of HI that we have is going to be double whatever the I2 and H2 are respectively. Okay, so if the 1.87 times 10 to the negative third is 2x, okay, the values that we have for I2 and H2 are going to be x and x respectively. Now notice, because we are decreasing the amount of H2 in the reaction as it progresses, we have a minus sign in front of the x. And because we are decreasing the amount of I2 in the reaction progression, we also have a minus there. And notice there's a plus sign in front of the 2x. Because obviously we're gaining HI in this reaction. Okay, so if 1.87 times 10 to the negative third is equal to 2x, x by itself is going to be equal to 9.35 times 10 to the negative fourth. Okay, and we can therefore figure out basically our equilibrium values based on the initial values that we were given. So you can see them here and here. Okay, and basically the change that's going to occur in those values. Okay, so our equilibrium is going to be established by the relationship between our initial and change values from the ICE table. Okay, so if we look at what we've done here, we've taken our initial value, and subtracted the change that we see here. So 1 times 10 to the negative 3, okay, minus 9.35 times 10 to the negative 4th, and that gives us 6.5 times 10 to the negative 5th as the concentration value of H2 at equilibrium. We do the same process for I2, and that gives us our value for I2 at equilibrium. So now that we have our H2, I2, and HI, we can then plug our equilibrium values into our equilibrium expression to get our equilibrium constant. Okay, so here we are again with our equilibrium expression that we wrote earlier. Okay, we plug in the appropriate values from the ICE table, and we subsequently calculate that our Kc value is equal to 51. Okay, so the steps are pretty simple. First thing you do is make sure that you have a balanced equation. The next thing you do is write your equilibrium expression. You then set up your ICE table and plug in any appropriate values that you have been given. You then take the values that you've been given and figure out the changes that are going to occur for each reactant and product on the ICE table. And then you subsequently plug your numbers in and figure out your equilibrium concentrations for each of the reactants and products. You then plug it into your equilibrium expression and get your Kc value. So if you follow this rule or this process, you will subsequently be able to figure out what it is that the equilibrium constant value actually is. Now we can apply these types of problems to values that include pressure. So instead of Kc, obviously we'd be calculating for Kp, and we'd be plugging in partial pressures as opposed to molarity values. But overall you would treat that exactly the same.